Hello, welcome to another lecture on graphing rational functions. We have a rational function here, y equals x minus 4 over x plus 2, and we want to draw the sketch of this function. The very first thing we're going to do is to find the domain of the function. If we do not know where a function is defined, where it's not defined, then we will not be able to draw the graph of the function. And in rational functions, you know that there is a famous restriction, and that's the fact that the denominator cannot equal to 0. So by setting the denominator not equal to 0, we're going to say x cannot equal to negative 2. So other than this non-permissible value of the function, we are okay with any other x value. Therefore, the domain of the function is the set of real numbers except that x cannot equal to negative 2. Next, we are going to perform an intercept analysis. So we want to know where the graph intersects the x-axis, where the graph intersects the y-axis. So we're going to set x equal to 0. And then when you do that, you get 0 minus 4, 0 plus 2. You end up with negative 2. This means that the y-intercept of this graph of rational function is going to be negative 2. So the y-intercept is at negative 2. We can, of course, plot that point. So we know that the graph should intersect the y-axis at negative 2. Next, we're going to set y equal to 0 for the purpose of finding the x-intercept this time, or we call it zeros of the function. So in that case, you know that a fraction equals 0 whose numerator is equal to 0. So you get x minus 4 equals 0, where you get x equals 4. So that is the x-intercept of this rational function. And we can immediately plot that, of course. So we know the x-intercept, we know the y-intercept, we know where the graph intersects the two x and y axes. So domain analysis, intercept analysis. Now we perform an asymptote analysis. Degree of the top, degree of the polynomial in the top, in the numerator, is 1, and degree of the polynomial in the denominator is also 1. We have linear functions basically in the numerator and the denominator. So since the degrees are the same, then in that case, the equation of the horizontal asymptote would be y equals the ratio of the leading coefficients, which in this case are both 1. So 1 over 1 is 1. So we're going to say horizontal asymptote, the equation is y equals 1, and the vertical asymptote is found by setting the denominator equal to 0. So if you set the denominator equal to 0, clearly x equals negative 2 would be that vertical asymptote's equation. So we're going to draw x equals negative 2, the vertical asymptote, and y equals 1, the horizontal asymptote. And we do not have any oblique or slant asymptote here for an obvious reason, because the degree of the top is not 1 more than the degree of the bottom. So here I'm going to say slant asymptote, and my analysis is none. So this is the asymptote analysis, intercept analysis, domain analysis. And as we move on, we learn more and more about the properties of this function. Next, we want to know the behavior of the graph at a neighborhood of its vertical asymptote. So we want to know what is happening to the graph when the graph is, when x approaches from left-hand side towards negative 2. So we're going to say if x approaches negative 2 from left side, so let's say we select something close to negative 2 on the left-hand side, such as negative 2.01. So if you select negative 2.01, the denominator is going to be negative, but very close to 0. The numerator is going to be negative. So negative divided by negative is going to be positive. Therefore, we will end up with a huge positive value. That is, we can say y approaches positive infinity. The reason is because the denominator gets smaller and smaller and smaller. The denominator becomes very, very close to 0 as x approaches negative 2. Then when the denominator of a fraction gets extremely small, the value of the whole fraction tends to be very, very large, very logically speaking. So we know what's happening on the left-hand side of the vertical asymptote. So the graph is supposed to behave like this. On the right-hand side, when x approaches -2 from right-hand side, we can select some value close to -2, such as -1.99. When you plug in -1.99 here, the denominator becomes positive, but positive 0. I mean, a positive number, a small positive number that is close to 0. The numerator is going to be negative, so negative divided by positive is going to be negative, but this negative number for the value of the whole fraction is like extremely large because its denominator is extremely small. Well, I said we selected -1.99, but we could have selected -1.999999. So that's like extremely close to -2, and making the denominator extremely close to 0, obviously. And when the denominator becomes extremely small, the value of the whole fraction becomes extremely large. We are touching upon concepts of calculus right here. Okay, so now I'm going to say y approaches -infinity, and that means on the right-hand side, the graph should behave something like this. Okay, and then what happens for the end behavior? What happens if x approaches positive infinity? So imagine if x is like 10 million. So 10 million minus 4 divided by 10 million plus 2 is going to be roughly equal to what? So on the right-hand side, if x approaches positive infinity, y is going to approach 1. And even if x approaches -10 million, again, y is going to approach 1. It's just like in one case, it's going to approach 1 from below. In one case, it's going to approach 1 from above. If you plug in here, for example, 10 million, okay, and 10 million minus 4 and divided by 10 million plus 2, you will end up a number that is very close to 1, but it's less than 1, such as 0.99999. But if you plug in like -10 million minus 4 and then -10 million plus 2, divided, find the answer, it's going to be again a number very close to 1. But this time it's going to be 1.00001, something like that. So a little bit more than 1, which means that on the left-hand side, the graph approaches its horizontal asymptote from above and not from below. Okay, so this was the analysis of the behavior of the graph at the neighborhood of its vertical asymptote, as well as the end behavior. So now I think we can put all this information together and draw the sketch of this function. So it's going to come down like this, and as we said, it's going to approach its horizontal asymptote on the left-hand side. And here, the graph starts increasing. It crosses the y-intercept that we did calculate earlier. Also, it passes through the x-intercept, and then it becomes closer and closer to the horizontal asymptote, as you clearly see. So, of course, these branches must be drawn perfectly symmetrical. So, perhaps I should have drawn this a little bit larger, but these two branches of the graph are totally symmetrical with respect to the point of intersection of the horizontal and vertical asymptotes. So with respect to this point, these are totally symmetrical if you draw them like meticulously. So perhaps I should have drawn this like a little bit to the left so that they're like really symmetrical with respect to the point of intersection of the asymptotes. So this is a more realistic graph. Of course, we can use technology that is graphing calculators, computers, different applications you can use, and your graph would be much more accurate. These types of functions are also called homographic functions, not in the textbook. And the name of the graph is a hyperbola. And because of the symmetry I talked about, it's called the rectangular hyperbola or equilateral hyperbola. These are the different names that these particular special type of rational functions have when the top and bottom are, of course, linear functions. Interval of increase, we see that the graph is increasing from left to right, and then even to the right of the vertical asymptote, it continues increasing. So we're going to say the graph is increasing on the interval from -infinity all the way up to -2, and then from -2 all the way towards positive infinity. But at -2, there's a gap there. There's this vertical asymptote. And these two intervals of increase must be sort of combined together, but we cannot add them up because these are not numbers. We're talking about sets of numbers. We're talking about intervals of numbers. Therefore, we cannot add them. Instead, we take the union of those two intervals or those two sets. And the symbol for the union looks like this, as you might already know. So that's the intervals of increase, and the function is never decreasing at all. So we're going to say there is no interval of decrease, and it's not your fault. Positive over what interval? Well, you see the whole graph is above the x-axis in the positive region, all the way up to the x-intercept of, all the way up to, I would say, all the way up to the vertical asymptote. After that, to the right of the vertical asymptote, it's below the x-axis in the negative region, all the way up to the x-intercept of 4. After the x-intercept of 4, again, the graph goes above the x-axis in the positive region. So interval, like positive interval, would be from negative infinity all the way to negative 2, okay? And then from 4 all the way to positive infinity again. So we take the union of those two. The only part that the graph is below the x-axis in the negative region is from negative 2 up to 4, of course, okay? So negative 2 up to 4, that is the interval of negative, we call it. So interval of positive, negative infinity, comma negative 2, union of that interval with 4, comma positive infinity, and then the function is negative over the interval from negative to 4, where you saw what happened. The graph was completely below the x-axis from negative 2 up to 4. Regarding the range of the function, so you see that any point you select on the graph of the function might have a positive y value more than 1, or it might have a positive value less than 1, or it might have 0 at the x-intercept of 4, or it may have any kind of y coordinate which is negative below the x-axis. So you see that y can be like any number you name it, except one value, and that is y equals 1 exactly itself, because the graph does not touch its horizontal asymptote, does not cross it. I'm not saying always is like that, but for this kind of functions, it's always like this. But there may be other rational functions where the graph intersects its horizontal asymptote. That is a possibility in general if we speak about them. So I'm going to say y cannot equal to 1, but other than that, any real number, that will be part of the range set of the function. So that's how we draw the graph of a rational function, and we identify all these properties. I hope you understood how we draw the graphs of rational functions of the form f of x, which is in the form of p of x over q of x, and p of x and q of x are nothing but polynomials of different degrees. In this case, of course, we have both numerator and denominator linear functions. In the next lectures, maybe we will talk more about curve sketching. Keep practicing. Thank you.